Alright guys, so this is the last of our Flip the Classroom videos for 6.2. In this video we're going to talk about vectors in the real world, and some of the topics we're going to talk about in this video can be applied to some of the word problems from 6.1. So after looking at this guy, you might want to take a second look at a couple of those word problems. Okay, so when we're talking about vectors in the real world, we're going to be talking about two different kinds of vectors. The first vector we're going to talk about is a distance vector. And with a distance vector, we are literally talking about an arrow that represents a distance traveled in a certain direction. So right here, we're going to take some direction as being 0 degrees, right? And the amount of rotation from that 0 degrees would be our direction theta. And the magnitude of our distance vector, let's call it a capital D. The magnitude of our distance vector is literally going to be the distance that some object travels, right? So right here, if we want to represent this vector in component form, we could say that we have a scalar of the magnitude of the distance, right, or the length of the distance, times cosine of theta as the horizontal component, and the scalar of the magnitude of the distance times sine theta for the vertical component. So that's the first kind of vector. The second kind of vector we're going to look at is a force vector. So right here, with a force vector, we're no longer talking about magnitude as representing literal distance, right? We can say similarly that direction is going to be some amount of rotation, theta, from a direction we consider to be 0 degrees, right? But right here, for our force vector, we would consider magnitude to be some amount of force applied in that direction. So right here, magnitude of a force vector is going to be a force applied in a direction, right? And in general, right here, what we might think of is this. This can be represented as us pushing against an object in a certain direction, where we might consider force to be in terms of pounds, or right here, we could also consider it to be a ball thrown in a certain direction where the force is some miles per hour. But in general, it's not the magnitude of the vector is no longer going to represent a literal distance. Instead, it's going to represent a force applied in that distance. And right here, what we can say is we can represent our vector in component form in the same way by multiplying the scalar of the force times cosine of our direction theta for the horizontal component, and the magnitude of the force times sine of theta for our vertical component. Now right here, we're going to be able to sort of use these two different types of vectors to plug into some formulas and answer some questions for us. So let's take a look at that. The first thing we're going to use these two different types of vectors to define is work. And we say that if F is a constant force whose direction is the same as the direction of a vector AB, then the work W done by F, the force, in moving an object from A to B is given by the magnitude of the force times the magnitude of the vector AB. Now, the vector AB is representing a distance. This right here is a distance vector. And of course, our force is a force vector, right? So right here, we might think about this as basically being us maybe pushing an object, right, from a point A to a point B across a floor, right? So let's say, if we're sort of looking at ourselves, pushing, let's say, a box across a floor, right, then right here we would be applying a constant force to that box, pushing it across a floor from a point A to a point B, and us applying the vector of force and moving that box from A to B is the work. So right here, you push a box with a force F of 10 pounds forward 7 feet across a floor. So right here, that 7 feet is, of course, the magnitude of a distance from A to B, right? And of course, we can say that the magnitude of the force is 10 pounds. So why don't you guys go ahead and determine the work done on that box to move it 7 feet across the floor when we're pushing with a force, constant force of 10 pounds. We'll pause the video and give this a shot. All right, guys, so right here we've got our little formula. We're pushing on that box directly. And right here what we're saying is that work is going to be the magnitude of force times the magnitude of the distance that we apply that force in. So right here we've got 10 times 7, and that would be 70, and we call these feet pounds, where we're talking about the distance as feet and pounds as the force applied. So right here, this is when we're pushing directly on an object in a direction, right? If F is a constant in any direction, if our force F is a constant in any direction, then the work W done by F in moving an object from A to B would be either the dot product of our force vector and our distance vector AB, or the magnitude of the force times the magnitude of the distance times cosine of theta, where theta is the angle between the vectors. So right here, what we can do is sort of look at a word problem to sort of get an idea of what we're seeing here. And in general right here, what we see is we are looking at a problem where we are finding the work done by a 10-pound force acting in the direction of 1, 2, the component vector 1, 2, in moving an object from A, the ordered pair 0, 0, to B, the ordered pair 7, 0. So basically right here what we're talking about is putting a problem on the XY axis, where right here our point A is the origin, 0, 0, and our point B is basically 7 units down the x-axis. So right here we've got 7, 0, right? Now this of course allows us to identify our distance vector in component form as 7, 0, right? So that would be that distance vector right there. Now right here we've got our force vector as having a magnitude of 10 pounds, right? And right here a direction that is basically the direction of the vector 1, 2. Now right here we can sort of plot out that vector, but we want to keep in mind that the magnitude of this vector is not the force. The magnitude of this vector is not representing our 10 pounds. Really all we're taking from this vector is the direction. So we've got a force of 10 pounds operating in this direction over an interval, right, where we're pushing basically for that 7 units. So right here, what we want to do is take theta from our component vector right here. So right here we've got a couple different methods of doing that. In general, if we think about this vector, right, as creating a reference triangle with the vertical component as being the opposite side and the horizontal component as being the vertical side, we can basically determine the angle between our two vectors, theta, with the tan function, because we know that tan of that angle theta in the reference triangle is going to be the opposite over the adjacent, or 2 over 1. So right here, that means that theta itself is going to be inverse tan of 2. Right? So right here, we're able to get our angle theta in this way, right? And if we're looking at the easiest way to determine the work done between our two equations, it looks like we're closest to this equation right here. We've already got the magnitude of our force as 10 pounds. The magnitude of our vector, of our distance vector, AB, isn't going to be too tough to determine. Right here we can say we're moving 7 units along the x-axis, so the distance there is just going to be 7 units. And right here we can determine the angle theta, right, from inverse tan of 2, which is the ratio of the opposite to the adjacent for the reference triangle we've created with our direction vector 1, 2. So right here, what I want you guys to do is to put all this together and come up with the work done on the object. And we'll talk a little bit about how we get this after you do this. So go ahead and pause the video and give this one a shot. All right, guys, so looking at this one, we've got the magnitude of our force right there. We've got the magnitude of our distance, and we've got cosine of 63 degrees, which is our inverse tan of 2. And so right here, we can evaluate 10 times 7 times cosine of 63.43 degrees, and that is going to give us the work done of 31.31, and then we would call these right here unit pounds. So first we're listing the unit of distance, and then we're listing the unit of force. Now, right here, one thing that we can think about as we're looking at this problem is right here. If we've got that force vector, let's say we can represent that force vector as sort of something longer than our vector right here, 1, 2, right? And that force vector is not entirely working in the same direction that we're moving our object, right? Which is basically the direction along the x-axis. So right here, the only thing that's moving the object is the amount of the force that is moving in the direction that the object is moving in. So right here, what we can say is that really, that's the projection of our force vector onto our distance vector. So right here, let's go ahead and say AB is some distance vector, d, right? And really what we're seeing here is basically the projection of force onto distance, right? And it's that magnitude, that's the sort of force we're applying in that direction, times the magnitude of the distance, right? And this basically is the same work problem we saw from before. Well, right here, what we talked about before was the dot product is actually the product of the magnitude of the vector, right, in the direction we're going in, times the projection of the other vector onto that vector, right? So really, this is the dot product of force and distance, which we sort of written as AB, right? But in general, that's sort of how we get this formula right here. We might talk a little bit more about how we get this formula right here. We'll look at some word problems tomorrow. I think one thing that I want to make sure everybody's pretty good with is going from component form and deriving the angle. So that's maybe something we look at a little bit more tomorrow, and maybe some other word problems as well. This is all 3 videos, and we'll do a worksheet tomorrow. Okay, guys, good work.